Alright guys, so in chapter 7 we're gonna learn about more about the dislocations and strengthening mechanisms. So I told you before how important the dislocations are when we were looking at the defects in metallic structures. And I told you also the reason the materials can deform plastically, meaning permanently, is because of the existence of dislocations. So we're gonna learn what is the relationship between dislocation and the deformation, and also we're gonna learn how the crystal structure of a metal affects the mechanical properties, like if it's BCC, FCC, HCP, is there a difference depending on the crystal structure and the behavior, and if there is, then why? And then dislocation motion affects all kinds of mechanical properties, just not only strength. Okay, so we're gonna learn this relationship between the dislocation motion and mechanical properties. So with that knowledge in mind, then how can we increase the strength and hardness of metals or their alloys? Because at the end, I know dislocations are responsible for plastic deformation, permanent change shape, and if I don't want my material to change shape permanently or want it to require more strength, then what should I do basically? How can I increase the strength and hardness? And after that, we're gonna see we can also change mechanical properties by heat treatments, and we're gonna see how heat treatments affect the properties. So I guess I told you this before, but for plastic or permanent deformation to happen, because we know there is elastic deformation by stretching the bonds between, and it is temporary, and there is the plastic deformation which was permanent. So I might have told you guys this before, but basically the plastic deformation requires large number of atoms to move in response to an applied stress. So people try to understand what is the strength that is required to move atom layers slide over each other. Theoretically, they wanted to calculate that, of course assuming the bonds have to be ruptured and then reformed. And then those theoretical calculations showed very high strength values compared to what we observe in reality. So theoretically, we are predicting material requires much higher stress levels in order to permanently shape them, but in reality they don't require that much stress. So this is the reason the dislocation theory was basically established, because it was figured out that when we observe under microscope, actually the dislocations are the ones moving inside the material and are the main reasons we observe a macroscopic change in the material. Okay, macroscopic shape change in a material. So we can say then plastic deformation happens with dislocation motion. It is not like elastic deformations, like where the bonds between the atoms stretch and then comes back. Plastic deformation is happening with this dislocation of motion when we apply the stresses. And these dislocations we have learned edge screw mixed. Okay, so I think we also call this process slip. So remember to observe a visual change in the shape of a material is we need to have like large number of dislocations move at the same time. So we are seeing here in the image, right, how this dislocation moves and how we observe a change shape. This is just for a single dislocation, but you need to think about like millions of them moving at the same time, which will cause a visual change in the structure. So in figure A, we are seeing the edge dislocation, and we now know the dislocation line. And we are also shown the slip plane, where the slip of this dislocation happens. Okay, so we need to, in order for the dislocation move, you need to apply shear stresses. Okay, so with the shear stresses applied to a material, you can see, okay, with the shear stresses applied to the material, dislocation will start to move when it has enough energy to move. Okay, so you see it is now in place A, and in the next figure B, it is moving the place of B, right? So for it to happen, these bonds have to rupture and then form with the layer A, like this. This way, the extra half plane of atoms seems like it moved to place of B. Okay, so the same thing happened. These bonds will break, these bonds will form, and now C is the extra half plane of atoms. Then it moves through the structure like this. At the end, the dislocation motion will stop when it reaches the outside. So it goes outside of your lattice like this. And for just dislocation motion of just one dislocation moving like this will cause a change shape, but this is on the atomic size, right? So that's why we need millions of them to move in the structure, forming visual deformation in the material. And this process basically is called slip. And the plane where the dislocation moves, right, moves on, then it is called the slip plane. So we have slip process, and the slip happens on the slip plane. So I need to mention, which is important, is the applied shear stress should be sufficient enough to start this motion. So there is a magnitude of shear stress that will start the dislocation motion, that will start the deformation. Remember, we called this yield strength. So when we reached the yield strength, plastic deformation was happening, right? So that means when you reach the yield strength, the shear stresses are generated inside the material, which will then reach to a certain volume that is capable of making dislocation move inside the material, basically. Dislocation motion can be explained with the motion of a caterpillar. So caterpillar forms a hump, near its posterior end by pulling in its last pair of legs a unit length leg distance, and the hump is then propelled, right? The hump is then propelled forward by repeating the lifting and shifting of leg pairs. When the hump reaches the anterior end, the entire caterpillar has moved forward by the leg separation distance. So you can understand that the caterpillar here doesn't move by removing all its legs, right? Because it will require a lot of energy. It is just moving the legs step by step and pushing it forward. And this is an analogy given to us to understand the dislocation motion. So other than taking away all your legs from the floor, basically what it does is only takes a small part of legs forming the hump, and then push that hump forward, and then he moves one atomic distance, or he moves one step, okay, and continues to do that and keep moving. So there is edge and screw dislocations, but many times in materials they exist as mixed. So we also learn mix of edge and screw dislocations, right? So let's see how screw dislocations move in response to applied stress, and compare it with the edge dislocation. And in the first figure we are seeing that the edge dislocation moving in the direction of the applied shear stress, because the shear stress are the stresses applied on the surfaces like that, and the dislocation here is moving in a direction that is parallel, in the same direction, right? And this is the final shape change we observe here. When it comes to the screw dislocations, on the other hand, when the shear stresses are applied, the dislocation motion is perpendicular to that applied shear stresses. However, in the end, what we are seeing, the net plastic deformation for the motion of both dislocations, they are the same, because you can compare these two and they are the same. Okay, one just moving in the direction of the stress, one is moving perpendicular to the applied stress. So when it comes to mixed, then mixed is neither perpendicular nor parallel. It is in between. Okay, it is in between. So where does these dislocations come from? So they can be introduced during the processing of the material. For example, we do casting for metals. There is the molten metal, and then it solidifies. So during solidification, these defects can form. During plastic deformation, the number of these defects increase. In fact, when we do deformation, we are increasing the number of dislocations. And so the number of dislocations, we call it dislocation density in a material. And dislocation density increases as we expose the material to deformations, processing, and thermal heat treatments. Okay, the dislocation density changes with what type of the manufacturing technique the material is exposed to. And please guys, also watch the videos I send you, because those have animation, microscopic images, how these dislocations move and how their number increases in the structure. Okay, it's going to show you dislocation generation as we keep deforming the material. So it is not a constant number. The number of dislocations always change, even if when you are trying to deform it. It is why actually the strain hardening happens. We're gonna see, because the number of dislocations increase as we deform the material, and those dislocation density increase, the dislocations will be starting to interact with each other, prevent each other's motion. Therefore, the strength of the material increases. Think about if there are obstacles more in the way of dislocations, you have to push it harder and harder to move. Therefore, you need to increase the strength more and more to be able to keep pushing the dislocation, get over that obstacle. So the idea of strengthening is, as we introduced more obstacles to the motion of dislocation, I have to push them more, increase the stresses of the that is applied to the material to be able to push these, or to be able to make these dislocations get over those obstacles. So this way I am strengthening the material. Okay, now let's see with what different types of materials, what are the dislocation characteristics. Okay, in metals, because of the nature of metallic bonding, which we know, the dislocations easily move because the strength of these metallic bonds compared to covalent and ionic, it is less stronger than those, right? Therefore, remember also when the dislocation is moving, the bonds has to break and then form again and again. So here we are seeing in copper, aluminum, iron, these are the metals. Dislocation motion is relatively easy compared to other type of materials. And we learned metallic bonding is non-directional, and this also makes this motion easy. And then what happens, the slip, the deformation happens usually in closed packed planes and directions. So it was figured out basically closed packed planes and those directions will require the less amount of energy for dislocation to be able to move. So when you reach a certain stress level, the dislocations will start to move on the close packed planes and directions. So ceramics we know covalently bonded, and silicon, diamond are examples of ceramics, and this type of bonding is very strong and it makes the dislocation harder to move in the structure. It requires a lot of strength to be able to get over these strong atomic bonds. And we also know covalent bonding is directional, meaning atoms sometimes need to approach to each other at only certain directions, right? So of course, besides covalent, there are ionic bonds in the ceramics, and these examples such as sodium chloride, magnesium oxide, these are ceramics that are ionically bonded. And this motion in these systems are also difficult, dislocation motion, because again these are strong bonds. And remember, there are ions, right? Positive and negatively charged. And if you try to slide one layer over another, these negative charges has to come together because the planes are slipping over each other. But of course they will repel each other, and also this creates few number of slip systems, deformation systems basically, and then it makes the dislocation more difficult in ionically bonded structures, requires more energy, more stress levels. So when we say slip system, we are saying it is the combination of the slip plane and the slip direction. Together they form slip systems. Okay. So there can be different type of slip systems in the structures, and we're gonna see that, okay? Oh, right here. So as I said, combination of the slip plane and slip direction gives us the slip system. So the slip plane is the plane, right? We learned planes, right? 1, 0, 0, 1, 1, 1 in a crystalline structure. So this is the crystalline plane on which the slip occurs most easily, meaning it will require the least amount of energy for dislocations to move. And these are the planes with most packing. So the plane with high planar density will provide the easiest route for dislocations to slide. So in general, you need to know dislocations do not move with the same degree of ease in all crystallographic planes and in all crystallographic directions. They will prefer a plane and they will prefer specific direction. And the combination of the slip plane and the slip direction is our slip systems. And the slip system will depend on what type of crystal structure you have, because FCCs, BCCs, remember they have different mostly packed planes and directions, right? So therefore the slip system will depend on if you have FCC, BCC, what type of structure you have. So if you have planes in that structure with the high planar density, most packing, those are providing less distortion for dislocation to be able to move, okay? Smooth ride. So the dislocation will prefer those slip systems in the structures. So always the slip plane will be the one with densest atomic packing, and the slip direction on that plane will be the direction where you have the most closely packed atoms, okay, where you have the highest linear density. And we have learned what planar and linear atomic densities are. We were able to calculate those numbers for different directions and planes for different crystalline structures in chapter 3. So now if we look at individually the crystal structures and the slip systems in those, let's start with FCC. So we remember the unit cell of a face-centered cubic crystal structure, right? And think about which plane we have the densest atomic packing, and that is gonna be 111 plane and its family, okay? So that is showing us is this in the image. This is the 111 plane where the slip happens, and on that plane which which direction has the highest linear density. Okay, and we figured it out that is 110 direction. And be careful of the brackets, like this is showing us on this plane slip will happen on those mostly densely packed directions. Okay. So each unit cell contains 4 of these 111 planes, right? You can draw another one right there. Then here, right? Okay. So 4 of these 111 is possible for each unit cell. And each 111 plane we just seen have 3 of these most densely packed direction, which is 111, right? 3 of these 110. 3 of these 110. So that gives us the combination of 12 slip systems in FCC structure. Okay. So you can see how they define the slip system. It is plane and the direction. So if you say 111 and 110, this is the definition of the slip system in the FCC structure, and we have, by combination, we have 12 of possible of these slip systems in the FCC structure. And you also seen that just one slip plane can have more than one slip direction. Therefore, it makes several slip systems exist in a particular crystal structure. Now at this point, I suggest you guys to go to table 7.1 in your book, and then you will see what are the possible slip systems for other crystal structures like BCC and HCP. In BCC, slip can happen more than one family of planes. So 110, 211, 321, those are all possible planes that slip can happen. And for BCC also, 12 slip system are identified, at least 12. So therefore, metals with FCC and BCC crystal structures, they have relatively large number of slip systems. That makes them quite ductile because you can easily deform them in various slip systems, right? Think about it. Remember, with the slip, the deformation happens, and if you have a relatively high number of slip system where this dislocation motion can take place, that makes the material easily deformable, ductile material. Okay, so, and we can say FCC and BCC, these are relatively ductile materials compared to HCP metals, because HCP, if you look at the table, you're going to see it has much less amount of slip system possible due to its structure, and therefore HCP metals are therefore brittle, quite brittle, not ductile like FCC and BCC. Therefore, the number of slip systems directly affect the behavior. If it's going to be ductile, if it's going to be brittle, that is related to the number of slip systems. Some examples maybe to keep in mind. Aluminum, copper, nickel, these are FCCs. So you can understand now why they are ductile. And for BCC, tungsten, molybdenum, and these materials, and alpha iron, they are BCC. For HCP metals, which are brittle, there is titanium, beryllium, zirconium, magnesium, cadmium, zinc. So that is the reason they are brittle compared to other ductile metals like aluminum, copper, iron, etc. So now you understand the reason behind the behavior of these materials. So now we have learned for slip to happen, we need to apply shear stresses to the material. So how does shear stresses emerge in a material? When we apply a tensile stress, right? So when we apply a tensile force to the material, as you see in the figure, actually this tensile force has shear components, like force components. These components are called result shear stresses. Let me write it down. And now I'm gonna show you what are the components of these tensile force. Okay, so we have our so of course here we are working in a single crystal for now, because this will simplify the things, because in single crystals, remember, all atoms are in the same direction. So this way we can understand. It is because in polycrystals all grains will have different direction of atoms, so all will have slip planes that will be slip system that will be different direction to each other, randomly distributed. Okay, so let us just consider a simple single crystal, so we understand how we have force components and how shear is generated, and shear is exposed to the layers of atoms, and therefore how deformation happens. So let's look at the result shear stresses. Okay, so this is the cross-sectional area where we apply the force, and this is A. Okay, and then all right, I'm sorry if there is background noise. So here we need to understand the stress component. It's not gonna be perpendicular or parallel to the stress direction. Okay, so it's gonna be inside the material at a certain angle. Let's say this is R, so the shear here is generated in this plane here, and the cross-sectional area here is A prime, and so on that plane we have the slip direction. Okay, and this one is direction normal to that A prime, and here is our force, right? So the angle here in between the force and the slip direction, this is given as lambda here. And this between these are the force and then the normal to A prime, the angle is phi. Okay. So based on that, we can separate the force into its components. First of all, we need to understand from geometric relationship basically, A prime is equal to A over cos phi. Because if you look at carefully, if this is the A, in though between these angles is also phi. So that means A prime times cos phi is equal to A. Right, we can write this from just the geometric relationships. What about the component of the force acting on that plane, parallel to that plane? That is force times cos lambda, right? This one. Okay, this is force times cos lambda. So we now know what are the forces acting on that area and what is the area, right? This was A prime and this is which was equal to A over cos phi, and this was of course F times cos lambda. So how we define the shear stress? Okay, how we define the shear stress? As always, we define the stress is equal to force over the area, right? Force over the area. So what is the force acting on that area? It is force times cos lambda over what is the area? A over cos. And you guys know now that force over area is actually normal stress, because that is, we are talking about the normal force, we are talking about the area perpendicular to that force. Okay, so that is your normal stress that you are applying. So therefore the equation is stress times normal stress times cos lambda times cos phi. Okay, so this is what that is. This is a relationship between the shear that is generated on that slip plane and with its relationship with the normal stress that is applied to the material. And this shear stress is called the result shear stress. Okay, let me tell you one thing here. Let's choose a color, different color. Okay. Anyhow, never mind. Let's go here. Okay, so remember we said that for dislocations to be able to move, there has to be certain amount of stress, there has to be certain amount of force that is given to the dislocation so it can get over the obstacles of these atomic bonds and move along the structure. So there has to be a certain stress level that needs to be reached so that dislocation moves inside the structure. And that stress level is called critical result shear stress, shown here, okay? shear stress with a subscript critical shear stress. So when you have resolved shear stresses that are equal to or bigger than this critical shear stress, now your dislocations can move inside the material. The typical values of those critical shear stresses are given. That is the minimum minimum shear stress level that you need to obtain in order to initiate the slip. And this is basically a property of the material. Okay. So this is where the yielding happens. So remember, the dislocation motion means once the dislocation motion starts, the plastic deformation happens. So we go from elastic to plastic because we reached a certain value of shear stress and the dislocation can now move. It moves mean that the yielding is happening and yield strength of materials are different. So that means also tells you the critical result shear stress that is necessary at least for the dislocations to move is gonna be different for different materials, and it is in the range of 0.1 to 10 megapascal. So we know for a certain crystal structure there will be multiple slip systems. So in a single crystal there will be multiple slip systems. Depending on if it's FCC, BCC, there will be number of slip systems, right? And a variety of orientations that the slip can happen. So which one is preferred? One of those slip systems is gonna be the preferred one, most favorable one. And that is the slip system that has the largest resolved shear stress. We call it maximum resolved shear stress. So on those slip systems, that is gonna be the most favorable slip systems, most favorably oriented slip systems, because this highest value of shear is achieved based on those angles like the lambda and phi. Based on that, the shear will have the highest value. So let me now tell the thing I'm trying to tell before. So the shear is, we looked at it, it was sigma times cos phi cos lambda. So you can write it down like this also. I mean, from cos and sin relationships. Let me see. Okay, let me write it down again here. I deleted the page accidentally. Anyhow, this here we have instead of that I can write instead of lambda I can write that. So this gives me, so when this relationship is maximized, okay, when you define phi as pi over 4, T is reaching the maximum value, okay, because it's becoming sigma over 2. And when phi is 0 or phi is 90 degree basically, so this is for 45 degree, these are 0 and 90 degrees, what happens? T, the shear is 0. So if you have a force and the planes where there is perpendicular and parallel to that force, those planes will not have any shear. Okay, and the shear is maximum when that angle is 45 degree to the applied force. Okay, so those planes where you reach the maximum of that are gonna be the most favorable slip system, most favorably oriented slip systems, because the result shear stresses will be the highest there, and that will be, of course, the possibility of that getting above the critical shear stress is much higher. That's why the slip happens on those planes when the result shear stress is the maximum. Okay. Then, of course, this also defines the yield strength, right? So the yield strength basically is when that shear stresses reaches the critical volume. That's when the slip happens, as I described. And you will see that when that shear is reaching the critical shear stress, critical result shear stress at those maximum value of these angles, yielding starts. So that is the definition of yield strength. So now in a single crystal, how do we change a macroscopic scale difference? And you see we will have parallel slip systems and in a single crystal, and on each of these planes large number of dislocations will move, not just one, right? And then we are observing this macroscopic shift that is visually can be seen. And these can be sometimes seen as slip lines. And please look at the video links I send you, because you will see some visually what are the slip lines look like. Okay, now I told you the maximum value of the angles has to be 45 and to be able to get the maximum value of the shear result shear stress. But we also need to know that they don't have to be, the sum of the angles don't have to be 90. Okay, that is just, if it is 90, like 45, that is giving us the maximum. But then it doesn't have to be 90, because it need not to be the case that the tensile axis, the slip plane normal, and the slip direction all lie in the same plane. So it doesn't mean this is 90. Okay, but we know that from the equation, if 45 is given to both angles, that is gonna give us the maximum. Okay, but it doesn't have to be 90. Okay, so now we have an example here. So there is a single crystal of a metal, and the critical result shear stress is 20.7. And what we exposing the material to is tensile stresses of 45. So will yielding occur when the angles are phi 60 and lambda is 35? If not, what stress is necessary? All right, so at those angles, with that tensile stress, the result shear stress is 18.4. All we had to do to find the result shear stress, just plug in into the equation. Okay, but the result shear stress we have is lower than the critical result shear stress, because the dislocation motion happens when we reach that critical result shear stress, or the yielding happens at that shear stress. If our volume is under that and we couldn't reach that stress level, the dislocation will not move, so no yielding. So the next question was, if not, what is the normal stress, the tensile stress we apply basically to achieve that critical result shear stress? And now we know the equation for the yielding to happen. Okay, so the yielding normal stress that needs to be applied is equal to critical result shear stress over cos lambda times cos phi. So this will give you the normal stress, the normal tensile stress you need to apply to reach that critical result shear stress at those angles. Okay, so therefore when we plug in the equation and calculate, we are seeing that yield strength of the material is 50.5 megapascal, but we have 45, and it tells you that you need to go above 50.5 megapascal to be able to start the yielding or the dislocation motion. So when it comes to polycrystalline materials, it is more complex because of the random crystallographic orientation of the different grains. So basically the direction of slip will be different from one grain to another. So we are seeing an image here of copper specimen, which is polycrystalline, and you can see the slip lines, right? In this case here. So for each grain, we are seeing the slip lines are in different orientations, because always the slip happens in the most favorable orientation, and that of course changes depending on your crystalline orientation in your grains. So we know that the slip occur, the slip systems that will be favorable are the ones that has reached the maximum result shear stress, and then when this result shear stress, the maximum result shear stress is bigger than the critical result shear stress, then the slip happens, because in the maximum value of that result shear stress increase the probability that it is bigger than the critical result shear stress. Those are the conditions that makes the slip planes favorable, and on those slip planes basically the deformation happens, and each grain is different atomic packing. Even if they're FCC, we know the 111 direction will be different in one grain compared to the another grain, and then this will cause different grains to deform in a different orientation. So it is a random deformation within the polycrystalline material. So when we compare polycrystalline metals with the single crystal, we know that polycrystalline materials require more stress levels, higher stress levels to initiate slip and yielding. And this is because of the geometric constraints that are imposed on the grains. Because there are no grain boundaries, there are no differences in the orientation in single crystals. So that the dislocations flow easily when you reach the most favorable condition. But in polycrystalline there are a lot of obstacles to the dislocation motion, starting from the grain boundaries and different orientation in grains, and therefore polycrystalline metals are stronger than their single crystal form. Okay. When we actually deform the materials, such as, let's say, a manufacturing technique called rolling, like we are deforming the material, the initially aqueous grains becomes elongated along the direction of the deformation, and we are seeing this in these microscopic images. And we are actually distorting the grain structure. When the grains elongated in this manner, when we change their shape, plastically deform them, that means the properties are gonna be more anisotropic, meaning depending on the direction the properties will change. It's not gonna be like a more isotropic situation where we have aqueous grains. Okay, so let's now look at strengthening mechanisms for metals. So we talked about that for a metal to deform plastically, the dislocations has to move, right? And what if I just stop their motion with some addition of obstacles in the structure? Then we need to apply more and more forces to come over those obstacles. So this is a way to strengthen the material. So since dislocations motion is responsible for the yielding to start, let me then stop those dislocations from moving. Then I need to apply more than the yield stress that is required without the obstacles. So properties such as strength, hardness, these are related to the dislocation motion. If you reduce the dislocation mobility, that means prevent them from moving, you are actually strengthening the material or hardening the material, because you need to apply more forces to cause dislocation motion. But if the dislocations are easily flowing through the material, not many obstacles, then it makes the metal weaker and softer. So on the background we hear the birds sabotaging my lecture recording. So we're gonna learn how we can introduce obstacles to the dislocations, and these gonna be grain size reduction, because the grain size, the more the grain boundaries, if you increase the grain size, more grain boundaries it means. The grain boundaries are where atoms, remember, are randomly oriented, and it requires more energy to cross from one grain to another, and we're gonna see it, okay? And then another way to stop dislocation motion is solid solution strengthening, meaning we introduce some particulates inside the material, and then those particulates can prevent dislocation from moving. And strain hardening is also called cold working, meaning you are changing the material at room temperature. So that's what cold means, okay? You are applying forces, working on the sample, and you are deforming it. Basically, think about the tensile test. We are deforming it. That is a cold work. And I told you guys there is this region, right? This region called strain hardening region, because there was the strain hardening exponent. So because the stress is so, as you see, I need to keep increasing the forces applied, because the material is getting stronger and stronger in that region, because the number of dislocations are increasing, and dislocations can be obstacles to each other. Think about so many people in one place. It is very difficult to move, right? So this is the same concept. All right, we are seeing the effect of grain sizes in the strengthening of metals. So we are seeing two different grains side by side in a polycrystalline material. There is the grain boundary, and there it goes, your dislocations moving, and it will try to pass from from the boundary to another grain, right? And this will require more energy than it was slipping before. So grain boundaries are barriers to dislocation motion. Of course, it's not going to be a smooth ride. This is a smooth ride, but when it comes here, there is a discontinuity of slip planes. First of all, slip planes are different in different grains, so the slip planes will change. Okay, the slip planes change direction, so there is a directional change, and that causes us basically the dislocation to require more energy to be able to pass from one grain to another. So the idea here is, if I reduce the grain size, that means because think about it, this is a large grains, this is grains that are smaller, right? So you see the surface area, the grain boundary area increased when we reduce the grain size. So reduce grain size means more barriers to dislocations, means increase in the yield strength, tensile strength, and hardness of the material. In summary, smaller your grains, stronger is your material, okay, harder is your material, and that is the conclusion. And how this yield strength depend on the grain size is explained to us with hole and patch equation. In that equation, we are seeing that how the yield strength depends on the grain diameter. It has some constants depending on what type of material you have. So next is strengthening with solid solution hardening or strengthening. So in order to understand why in solid solutions the material is getting stronger, we need to first understand the stresses that are created within the lattice due to the presence of dislocations. So this image is showing us clearly when you have a dislocation, extra half plane of atoms. When you are above that slip plane, there is a compression stresses generated in the system, because you are stressing the vicinity of that dislocation, right? But then under that slip plane there is tension, because then that extra half plane of atom presence of it is trying to separate what is below that slip plane. Okay, so that means above there are compressive stresses, below there is tensile stresses generated, but this is only around the dislocation, not in far away from the dislocation. Okay. Therefore, when you introduced small impurities like solid solution, like we were putting nickel in copper, for example, right? So when you actually add those impurities, what happens if they are, it depends on if they are smaller than the host atoms or bigger than the host atom. Let's say it is small, okay? And when you place in those small substitutional impurities, it also creates a stress around the atoms. So what happens? It creates tensile strains. Okay. Now, since the material will not want to stay in strained configuration because it needs to relax, right? Minimize the strains in the structure. That is what preferentially happen. So those tensile strains generated around the small impurity can be neutralized if this small particles move, small atoms move into the compression side of the dislocation. Because above the dislocation we know compressive stresses are happening, and on the other hand this presence of small impurities cause tensile stresses. So the impurity atom will intentionally go to and place on top of the slip plane to neutralize that tensile strain. Okay, so basically compression here, and this creates tension. So that means if they want to neutralize this effect, the structure doesn't want to be strained, right? They want to reduce the energies it has, because at the end when you are straining you are storing energy inside. So materials always want to go to a configuration where there is minimum energy. Therefore that tension causing impurity will go to compression causing dislocation plane. Therefore it neutralizes the effect of each other, relieving the stresses. Actually now it became difficult for dislocation to move, because the lattice strain must increase in order to dislocation to move away from those impurities. Therefore, putting substitutional impurities is strengthening the dislocations. By neutralizing these strains, we are preventing dislocations from moving. That means we require higher stress levels to be able to get over the obstacle of these small impurities. What if it's large impurities, right? The large ones will introduce compressive strains in the neighboring atoms. Similar to previous case, this compression will be neutralized, cancelled with the tension that is under the slip plane. Again, now more energies are necessary for that dislocation to be able to get over those impurities and move. Therefore, we are increasing the strength of the material. So please go to Virtual Material Science and Engineering website, which I send you guys the link, or you can Google it. Okay, we have looked at that website before. Previously, I sent you many links about that. And then what you can do is you can watch how these neutralizing effects work in the presence of impurity atoms. One such system can be alloying copper with nickel. Adding nickel to copper increases the yield strength and tensile strength. So if we look at the experimental results here, we are seeing both the yield strength and the tensile strength increases with the addition of nickel. Now, another way to increase the strength was strain hardening. So if we deform the metals at room temperature plastically, what happens is, I described to you guys, is strain hardening. So due to strain, it is hardening. It is getting strengthening. Okay. So, of course, you can calculate the percent amount of cold work, the deformation from the reduction of the cross-sectional area, which is basically the percent amount of cold work the material is exposed to, is A0 over AD over A0. Because from when you do, let's say rolling, okay, let's say rolling here, we are doing to change the shape of the material, to plastically deform the material, which material with a certain thickness A0 is introduced pushed in between the rolls, which at the end the material comes with a lower thickness, which is AD. So this tells you how much cold work you performed on the material because of the change in the cross-sectional area. As the amount of cold work increases, the yield strength increases, tensile strength increases, ductility decreases. Okay. How do we know? From experiments performed on, for example, low carbon steel. If we don't deform it at all, do cold work on it, this is the yield strength here. Okay, but if I do 4% cold work, the yield strength changes to here. If I do 24% cold work, yield strength changes here. Similar to that, ultimate tensile strength is also increasing. But how do we understand ductility decrease? Because it was able to deform to this much, to this extent. Now it is able to deform until here. Now when you increase the strength, it can only deform up to here. You are lowering the ductility. Okay, so how does dislocations interact with each other? So let's say two dislocations here in the image A are moving within the crystal, and then they can come across to each other. When they come across, what can happen is either they will repel each other or they will be attracted to each other. In the case where they repel each other is when their compression sides come together. right? They will repel each other, or their tension side is the same. So if they are moving along the same plane, they will repel each other, because the compression will repel, because always the compression will come together with the tension in order to neutralize those strain energies, because at the end you are creating energy, and because you are straining. Remember, under the stress strain curve we said energy is stored. So if you are stretching the bones, you are storing energy, and material wants to eliminate those stresses, energies inside the material. Okay, so but then what if positive and negative dislocations come together? Positive and negative edge dislocations come together, because then the compression part of the one of them will be attracted to the tension part. When they come together, they will neutralize its effect, right? The other, for this region, it's the same. Think about, there is extra half plane of atoms here coming from that one, and there is another extra half plane of atoms coming from this one. So what happened? You reached a perfect crystal. So you actually annihilated the effect of dislocation. There is no defect anymore. You have reached the perfect orientation, perfect crystal structure. This is called dislocation annihilation. Okay, positive and negative edge dislocation can cancel each other. So I told you guys, in strain hardening, when we do cold working on the sample, dislocation density is increasing and they became obstacles to each other. So dislocation density is defined as the total dislocation length over the unit volume. And the dislocation density calculation showed us, if we have an undeformed metal, it is in the range of 10 to the power of 5 to 10 to the power of 1 per millimeter squared. So dislocation density is increasing with increasing deformation, because you see, when they measured the dislocation density in a deformed metal, it increased. Here we see microscopic image of titanium after cold working. We are seeing the dislocations, number of dislocations are very high. You see each of these are dislocations, right there, there, and then there, and then you see how they interact, right? And then here. These are all defects in the structure. Okay, so as we increase the cold work, the dislocation density increase because of the dislocation generation. So this is a more advanced topic, how dislocations are generated. But I sent you guys a link, and you can watch through how the dislocations are actually created. Under microscope, they were able to monitor that. All right, as dislocation density increases, of course, the distance between them decreases, and then they interact with each other. So on average, dislocation to dislocation strain interactions are repulsive, like this case. Because they are on the same plane. So dislocation motion is therefore neutralized. It is hindered by the presence of other dislocations. Example: compute the yield and tensile strengths and ductility for a cylindrical copper specimen that has been cold worked by reducing its diameter from 15.2 mm to 12.2 mm. So what you need to do is calculate the percentage of the cold work. So the percent cold work is calculated from the areas, right? A naught minus AD over A naught. And of course this is cylindrical material, so the area is going to be pi r squared or pi d naught over 2 squared. So based on that and based on the given values, this is the amount of cold work. Now, we need to relate this cold work percentage to tensile yield and ductility. And this can only be done if you are given the experimental results and those graphs. Basically, based on how much cold work you have done, what is the corresponding strength values or what is the corresponding ductility values. So this information has to be given to you, right? So from the amount of cold work, which was 35, you find that number here in a cold work versus in a percent cold work versus the strength curve. You go and read the corresponding yield strength. So this much amount of cold work will create this much yield strength in the material. And you do the same for other parameters here, like tensile strength, okay, and ductility. So this way you can read the information about ductility and yield strength and tensile strength. Of course, these has to be experimentally obtained first. So what people do as a function of cold work, they are measuring the strength values or ductility values, and then they are plotting these curves. Now with using these curves, you can, by just looking at the amount of cold work, you can tell what strength value you can obtain. Okay, so heat treatment of cold work alloys. So think about it this way. We just learned that cold working on a sample makes it get stronger and stronger and stronger. So how can you keep working on the sample if it's getting stronger and stronger and stronger? Because then in your processing you need to apply more and more stresses, and then the material is becoming brittle because it is becoming more strong, and it makes it impossible for us to keep working on the sample due to economical reasons, due to the just reason of the material is becoming brittle. So there are heat treatments that has to be done, and this is called annealing. We can reverse the effects of cold work structure, and this way we can lower the strength and make the material more ductile. This way we can continue working on the sample. There are 3 stages of annealing process. The first one is recovery, and in the figure you are seeing how tensile strength, how ductility is changing as a function of annealing temperature, the temperature that we kept the sample, the cold work material. So in the recovery region, which shown with the blue, stresses are relieved, okay? So because we are straining the material with cold work, those stresses at rather low annealing temperatures, as we start from the room temperature and keep increasing, the first step happens here is the recovery. Those strains that is inside the structure are relieved, stresses, okay? And then in the second stage, which is the recrystallization, the most important stage here, is what happens, the deformed grain structure. Remember, when we do cold work, the grains were elongated, okay, and the number of dislocations in those grains increased. What happens, dislocations have now enough energy due to the temperature to rearrange themselves and neutralize themselves in the form of grain boundaries. And in the recrystallization, as the name implies, new grains, new crystals are gonna form from those damaged grains. And this will dramatically increase ductility while dramatically reducing the tensile strength. And what you can do, you can keep increasing the temperature, but as you keep increase the temperature, the grains will start to grow. So if you want to optimize, you can find a certain annealing temperature which will give you the best performance. Okay, so in the recovery stage, what happens is the reduction in dislocation density. So because, as I said, the stresses will be relieved, because when you have a dislocation, there are stresses, there are energies stored in the close vicinity of these dislocations, and we have seen, right, compression and tension. What will happen is, because now the dislocations with heat given enough energy, they want to move and neutralize themselves, okay? So what happens is the dislocation, annihilation, and then relieving of those stresses that were created due to the presence of dislocations. And how this can happen? They can either come together, maybe they're on the same slip plane, or they can do climbing. Basically, if they are not in the same slip plane, one of the dislocation has to move to the same slip plane so they can come together and annihilate. So all these possible. In the second scenario, what happens? The dislocation might not be able to move due to an obstacle, and then might diffuse, also called climb. So the gray atoms leave by vacancy diffusion, allowing dislocation to climb. Okay, so when the dislocation climbs, it can become in the same slip plane as the other one. Then they basically experience annihilation of those dislocations. Also remember, the vacancy diffusion is increasing as we increase the temperature, right? So what about recrystallization stage? As I told you guys, for new grains form, and those new grains now will have low dislocation density. They will be in small size, and it will be from the consumption and replacement of those cold work grains. And here we are seeing a cold work brass before the heat treatment, and you see the slip planes in the grains, and the grains are elongated, and we see the slip planes like that. What happens here, if you do heat treatment, 4 seconds of heat treatment at that temperature, you see along those damaged grains, we can still in the background, tiny grains start to nucleate. So this happens basically, let me see if there's an image. Okay, so basically what happens, the dislocations will have enough energy to rearrange themselves and neutralize themselves in the form of grain boundaries. That is what's happening, but you don't need to know that. That is more advanced information. And then dislocation density is therefore decreasing because the dislocations were already used in the forming of new and small grain boundaries. So basically you need to know that in the recrystallization, number of dislocations are decreasing, the grains are becoming new and in small in size, and this makes the material more ductile and therefore easy to deform. Now after 4 seconds, so think about just within 4 seconds it was like this, right? And now just add 4 more seconds within 8 seconds of that temperature, you see in microscopically all grains are now replaced. Basically the damaged grains are gone and now we have new fresh grains, small grains. So the definition of recrystallization temperature. What is the recrystallization temperature? It is the temperature at which the recrystallization reaches completion in 1 hour. So they did experiments, kept each type of material 1 hour, and then figured out that temperature. So this of course will depend on what type of material you have, but that is in the range of 0.6 times of the melting point and 0.3 times of the melting point. So then of course, as I said, depending on what type of metal you have, the recrystallization temperature will be different. It increases, recrystallization temperature increases with decreasing cold work, or recrystallization temperature decreases with increasing cold work, because increment in the cold work introduces already energy in the structure. So then you need to provide a little less for that crystallization to happen. So then your crystallization temperature decreases. And the purity of metal, if we look at the effect of it, the recrystallization temperature decreases with increasing purity. And this is the same if you have not pure metal, more obstacles inside. This create already energy storage inside the structure because of the strain around those impurities. Therefore, again, it will require a relatively less amount of thermal energy, less temperatures to be able to reach that recrystallization temperature. So there are 2 types of different processing techniques. We can either work on the room temperature and change the structure of the material, or we can do hot working. As we are deforming, we are also doing annealing. So this is also good because this way you can keep working on the sample due to the reasons I explained. So when you do cold working, you are working below the recrystallization temperature. When you are doing hot working, you are working above the recrystallization temperature. So annealing and deforming happening at the same time. So final stage of annealing is grain growth. If you continue to increase the temperature, so this was after 8 seconds. Now if I keep it at 15 minutes at that temperature, you see how the grains grow. Okay, so average grain size increase, small grains shrink, large grains continue to grow. Please check the website links I'm sending you for the animation of grain growth. Grain size has direct effect on the properties. If you have small grains, you have a material that is strong and tough at room temperatures. If you have large grains, this can have good creep resistance at relatively high temperatures. So of course, creep, what does that mean, right? It is a term we use to describe the plastic deformation at high temperatures, because sometimes you might be exposing your material to stresses that are lower than its yield strength, so you don't expect the material to change shape. However, material can still plastically deform, and this is called creep, because with the temperature, basically it affects the stresses required for the plastic deformation to happen. So some experimentally observed relationship between the average grain size and the time of the heat treatment, and that is given through this equation. So we look at the initial grain size, average grain diameter before heat treatment is d naught to the power of n, usually is 2, and then d to the power of n after the heat treatment, and this is equal to k times t. K is a constant depending on what type of material you have, and it is independent of the time, and the t is the time. So from this equation you can figure out dependence on the time to the grain size. So this is showing you the structure of grains, how they are changing throughout the annealing process. So we have cold work grains here, elongated, right, like this, and then in the recrystallization, when we are at the temperatures of recrystallization temperature, what happens is new grain starts to form. Okay, so with the completion of this new grain formation, if you continue with the heat, it will cause the grains to become bigger and bigger. Alright, problem is a cylindrical rod of brass in diameter of 10 millimeter will be cold work by drawing. Drawing is a processing technique again. So we are deforming plastically. The cross-sectional area is circular and then will be maintained during this plastic deformation. Okay. And a cold work tensile strength in excess of 380 megapascal and a ductility of at least 15% are desired. Furthermore, the final diameter must be 7.5. Okay, so the circular cross section will be the same, but its size is gonna change. Explain how this may be accomplished. So we have a material that has a diameter of 10 millimeter. After drawing, it will decrease to 7.5 millimeter, and this should give you the percentage of cold work. Okay, so we calculate the percentage of cold work from the change in the area of the cross section, which is circular. All right, we did it, and it is 43.8. And from experimental data that were given to us, if we know the percentage of cold work, we can figure out what the tensile strength is and what the ductility is. So they should put a ductility on the y-axis and tensile strength on the y-axis, like that. So we have seen that the material strength is 450, and the deformation is 6%. So we are requiring at least 15%. So we don't satisfy the conditions. Let's look at then to get a 380 megapascal tensile strength, what should be the amount of cold work? That is 12%. And to be able to get a 15% ductility, cold work should be 27% or shorter, because as you get smaller, as you see, you go above 15. Okay. So deformation criteria is your cold work should be somewhere between 12 to 27%. Okay, so to have a yield strength of 280, the diagram shows we need approximately 20% of cold work. So what we can do is do that. So if we do 20% of cold work, we would meet the first requirement. And from our equation of percentage of cold work, you can calculate the final diameter, because you know the initial diameter. So in your problem, in your equation, put the I, initial, and the cold work amount to satisfy the first condition. And then you have a diameter of 8.39 nanometer. A millimeter, not nanometer, millimeter. So this is if we do step-by-step cold working. Then we calculate basically in first stage what we need is 29.6% reduction cold work percentage, and then we can do heat treatment, and then again we can do cold work to achieve going from 8.39 to 7.5 millimeter in that second reduction. So this one we calculated from the second cold work, and then so we were able to satisfy, as the previous calculation, 20% cold work, and at the end the tensile strength is nearly 400, and then percent elongation is 20%. So in summary, we learned about plastic deformation, and we learned about this is happening with dislocations. We learned that dislocation slip in slip planes and along certain direction, most densely packed planes and directions, and how grain shape is affecting the properties. And we said strength is increased with dislocation, decreasing the dislocation mobility. How we can do that? We can change grain size, reduce it, do solid solution hardening or strain hardening. And to release the stresses and recover the grain structure, we can do annealing. Annealing is composed of recovery, recrystallization, grain growth. And with that process, we obtain softer and weaker material and more ductile. This way we can keep working on the sample, because sometimes you cannot achieve the whole cross-sectional area reduction, because the material you cannot apply enough stresses. The material cannot handle and become brittle. Therefore, You might need to do cold work, then annealing, and then cold work again to achieve the reduction in cross-sectional, desired reduction in cross-sectional area.